Turgeon here, bringing you physics from afar. This is another master equation. This one is for collisions, but actually it's for all systems that are isolated. And let's remember, an isolated system is one that's not influenced by an outside force. And let's remember that any system, you should probably write this down, any system is something that we define as the objects that we're interested in, and in particular, the objects that are going to interact with the other objects. So for collisions, the law of conservation of momentum is particularly useful. There were other situations like roller coasters, where the law of conservation of energy was particularly useful. Lowercase p is momentum, total before and after, the same. Momentum cannot be created or destroyed, it's only transferred. Now, what's interesting is the transferred part is hard to see here, but it's really, really cool and interesting to actually do the calculations and see why the momentum is transferred. Now, if you want an extra challenge, try to figure that out for yourself, like get all the numbers for a particular problem and try to figure out how the momentum was transferred. That's an interesting challenge, interesting algebraic challenge, and interesting physics challenge. Now, what you want to do is you want to write P total 1 equals P total 2. And then, but instead of like energy where there are a bunch of different types, it's all just momentum. But they're momentum of different moving objects. So moving object 1, mv, moving object 2, mv, moving object, moving object. All of this on the left side is before, all of this on the left side is after. Then you throw in a bunch of subscripts. The first object's mass, the second object's mass, first object's mass, second object's mass, velocity, 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 velocity. These little things are primes, kind of like in geometry when you did transformations and you wanted to locate points, but you wanted to like map points on the other points, but note that they are new. This is called the relative speed equation, also known as the relative velocity equation. This is for later. Don't worry about this now. I'm just showing you so you can sort of have a comprehensive collection of the momentum equations. This is also a really interesting thing. More details on that later. But I want to go through this particular momentum problem that we did today. You can read this. It's about the bag of gold. This is the diagram representing the bag of gold and the dot representing the freezing guy. They're both zero velocity. Then they have the velocity afterward where they both have a velocity. The velocity of the recoiling person is less than the velocity of the bag of gold because the bag of gold has less mass. So we write down the master equation, I'm immediately going to cross these out. These are zero because they're stationary. These are moving. 0 plus 0, put in the numbers, mass, mass, velocity. Note the direction. Note that this one comes out negative. As predicted, we're going to calculate the kinetic energy, write this down. Calculate the energies of each thing individually. Calculate individual objects. Do not try to combine objects when you calculate the energy unless maybe it was inelastic where they become one object like we're going to see in a minute. Also notice that kinetic energy is always going to come out positive. It's a scalar quantity. It has no particular direction, unlike momentum. 56.16 is the total kinetic energy. That was therefore the gain in kinetic energy because the original was 0. May seem kind of weird that we gain kinetic energy, but we don't gain or lose any momentum. It's true though. Let's look at inelastic collisions. This means they stick together. So again, P total 1 equals P total 2, but there's only one moving object after they stick together, they meld together. MT for total mass, VF for final velocity. There's only one object, it's the total mass, there's only one velocity. Let's call it the final. You can call it V2 if you want. Converting all of these to kilograms instead of grams. Plug, chug, solve, you get 0.33. Notice the negative. Notice that negative that's going to the left. Oh, kinetic energy, that's easy. Kinetic energy before, just calculate each individual one and add them up. Do not try to combine them. Here's the exception of when you can combine them because they became one object. You could calculate the kinetic energies of them individually and you'll still get 0.041. So this system lost kinetic energy. Ask yourself, where did that go? went into heat and sound. Elastic collisions, which we'll talk about later, when the two objects collide elastically, not inelastically. That's one of those things that in regular speech, people will be like, oh, I have a question. So in elastic collisions, wait, did you mean in collisions that are called elastic, or did you mean, are we talking about collisions that are inelastic? Gets confusing. For this kind of collision, you hear a smack, you hear a sound. There's vibrations and everything generated. Elastic collisions actually are silent. They don't really generate any sound. Facet of physics.